Hey everyone, this video is going to be on resonance structures. Just as a reminder, in resonance structures, it's the position of the atoms that remain fixed. It's only the electrons that move around. So some tips for drawing resonance structures is that you want to add your implicit hydrogens and lone pairs. Note your carbons with 4 single bonds because these carbons are sp3, so they are going to block your resonance. They are not going to participate themselves, and they can block other atoms from participating. Also, don't go too far down the rabbit hole and look for structures that are more insignificant contributors, and I'll explain what that means when we get into our examples. All right. So we're looking at this structure here, and we want to draw some resonance structures. Whenever you see a ring with alternating single and double bonds, immediately try and look for a resonance structure within that. But before we get started, we're going to go in and add our implicit hydrogens and lone pairs. So in the ring, the carbons that do not have any other attachments are going to have 1 hydrogen each because they have a double bond and a single bond. So these are all the implicit hydrogens that we're going to need. This nitrogen has a full octet, so we're not worried about adding any lone pairs to that. The oxygen on the right is going to need 2 lone pairs to complete its octet, which also makes its formal charge 0. And the oxygen on the top is going to need 6 lone pairs. 3 lone pairs, 6 electrons in total. Now, going back to the ring that we saw, when you have alternating double and single bonds, an easy resonance structure you can make is just to move each of the double bonds over by 1. So when you draw a new resonance structure, you want to put these double-sided arrows. That indicates that they're resonance structures. And you go ahead and you draw the structure. Now, when you draw new resonance structures, you don't have to put in the implicit hydrogens, but you do have to put in the lone pairs and the formal charges. That is very important. So we're going to go ahead and do that. And nothing else in the molecule changes right now. That's another tip with resonance structures. If you find a change that you can make, don't try and make multiple changes to find a new resonance structure. Just take each change one at a time, and that allows you to draw as many resonance structures as you can. All right, so now we're here. Once we've processed everything with that ring, the next thing we want to look for is see if we can move electrons from a negative charged atom to a positively charged atom. And we can do that with this oxygen and the nitrogen. So we can take a lone pair from the oxygen and draw an arrow moving it towards the bond. This means that now a double bond is going to form between the oxygen and that nitrogen. But then we run into an issue that the nitrogen has too many electrons. It's run over its octet. So we need to relieve that, and you can only really relieve that by moving a lone pair away from that atom or removing a pi electron from that atom. You can't really move a sigma bond or a single bond. So our only other option is to take the pi bond with the other oxygen and move it towards that oxygen. So now that we have made that change, we're going to draw our new molecule. So we formed a double bond and took away a lone pair from that oxygen on the top. And we turned that double bond with the oxygen on the right to a single bond and gave that oxygen an additional lone pair. So the nitrogen is still going to be positively charged and the oxygen is going to be negatively charged. All right. So now this is where we can start to get down the rabbit hole a little bit. So we could say, well, I could take this pi bond right here and move it right here to have that carbon form a double bond with the nitrogen, and then say, well, I need to relieve some electrons from that nitrogen, so I can take this double bond and move it back up to the oxygen. Now we can draw out what that structure looks like. This becomes a double bond. The oxygen on the top receives a new electron pair, so this becomes a negative charge. The oxygen on the right retains its negative charge. The nitrogen is going to have a positive formal charge. And this is where we really want to have our implicit hydrogens. If we look here, we see that this carbon is only bonded to one hydrogen. So since this carbon right here has one hydrogen bond and only two other single bonds, it will have a positive formal charge because it only has 3 bonds total. Now, while this is a resonance structure, it's not really going to be a significant contributor because, first off, this carbon doesn't even have a full octet anymore. It has 2 single bonds and another single bond to a hydrogen. So it only has 6 electrons, 6 valence electrons. And we've also created 2 new charges. We went from 2 charges on the molecule to now 4. So this is what we call an insignificant contributor. And the other 3 seem to be equally contributing to the molecule, and they are significant contributors because they are the best that we can do in this scenario. All the atoms have a full octet, and the charges are minimized, and the negative formal charge is on the more electronegative atom, the oxygen, as opposed to the nitrogen. So these 3 that are around these 3, so 1, 2, and 3, we would call these the more significant contributors. Now on a test, they will likely ask you more about the significant contributors. They will ask you to make sure that the resonance structures you draw contain only the significant contributors, so you don't want to go ahead and draw something like this. All right, for our next example, we're first going to add in the implicit hydrogens and lone pairs. So for this carbon on the end, it only has 1 single bond, so we know that it's actually bonded to 3 other hydrogens. This carbon right here needs 1 hydrogen because it has a double bond and a single bond. These 2 carbons are all good because they have a double bond and 2 single bonds. This carbon right here needs 2 hydrogens, and this carbon on the end needs 3 hydrogens. Now for lone pairs, this oxygen only has a single bond, so we know it's going to need 3 lone pairs, and the other 2 oxygens are going to need 2 lone pairs. Now, there's no ring that we can look at like last example, so we have to resort to the next thing, which is, can we move the negative charge away from the atom with it? So, if we try and take a lone pair and move it down to this carbon now has 2 double bonds and a single bond. So we need to relieve the other double bond somehow. And what we can do is move that double bond to the atom, so it turns from a bond to a lone pair. So we can draw out what that looks like. So now that we have moved the double bond to the lone pair on this carbon, it now has the negative formal charge. Because remember, the implicit hydrogen, it has 3 bonds and a lone pair. So that carbon is now going to have a negative formal charge. So now we have moved the negative formal charge from the oxygen to a carbon. When we look for another resonance structure we can draw, we can say, okay, we want to continue to move that negative charge away from the carbon. So we can go ahead and move it to this bond, making that a double bond. And now we have too many electrons on this carbon. So we can relieve that by moving the double bond away from that carbon towards the oxygen. So now we're going to get something like this. All right. Now, there's not much else we can do here because you might think we can continue to move that negative charge down the molecule, but that's where our carbons with 4 single bonds come into play. And those are this carbon, and this carbon. These are our blocking carbons, right? So if we try to move some electrons down to make a double bond potentially right there, there would be nowhere to move one of the lone pairs on the oxygen away, because if you tried to move a lone pair to right there to form a new double bond, this carbon would be overloaded and there's no double bond or lone pair to move away from that carbon. So that's why those blocking carbons can't contribute to resonance, and they help us identify when we need to stop with our resonance structures. Now, looking to see which one's the biggest contributor, I would say that if I label them 1, 2, and 3. 1 and 3 look the most similar because they have the negative formal charge on the oxygen, and it's just the only thing that's switched is the oxygen with the negative formal charge. Whereas structure 2 has a formal charge on the carbon. Now, they all have their octets full, so that's not a differing factor. The only differing factor is where the negative formal charge is. You want the negative formal charge to be on the atom that is more electronegative. So structures 1 and 3 are going to be more significant contributors compared to structure 2, because the negative formal charge is on the more electronegative atom. So when we're first looking at this molecule, we want to add in our implicit hydrogens. Starting at the left, we're only going to add in 2 because that carbon has a positive formal charge. So we know that it's going to only have 3 bonds total. Now, every other carbon, except for the other one on the end, has 1 implicit hydrogen because it has a double bond and a single bond. The carbon at the end will have 2 hydrogens because it only has a double bond. Now, the carbon with the positive formal charge, we call that a carbocation. And when you're looking at it for resonance, you basically just want to move the positive charge along the molecule and make as many different carbons as you can the carbocation. So the way we do that is you just move around the double bonds. I'm going to take this double bond right here and move it to that location. So when we redraw the molecule, we can see where the positive charge goes. So in this case, we can see that it'll go on this carbon. And because you want to remember your implicit hydrogens, right? This carbon only had 1 more bond, which was the hydrogen. So it had now it has 3 bonds total. So that's the carbon that's going to have the positive charge. We can try this one more time, taking this double bond, moving it over here to get our last resonance structure for this molecule here. And you can tell that the positive charge moves over here because this carbon had 2 more hydrogens on it, the implicit hydrogens from the start, so it would only have 3 bonds total, and that's why it has its positive formal charge. Regarding how big of a contributor it is, all of these carbons, all of these molecules have 1 carbon without a complete octet, and it's the only difference between them is the location of the positive charge. So in this case, they are all equal contributors. There's no one molecule here that is a more significant contributor than the others.